We're live and we're recording. Welcome back to another exam walkthrough. We're going to be going through 2024 October Unit 5, question number 14 and question number 16. Question number 16 is going to be your 6 marker. So we're going to be going through these two questions. You can pause the video, try out the questions yourself. And if you want to see me solve the question, you can watch the video. And if you just want to see the mark scheme and examiner report as well, you can go to the end of the video. I will show you the mark scheme and the examiner report. Now, I'm not going to read the full question. I want you to pause the video, read the question, and I'll just start answering the question so we don't waste too much time. So we know that from the question, after reading it, that the bubble is at the bottom of lake and then it is going to rise up. And then as it rises up, the diameter is going to be increasing. And the reason for this is going to be the change in temperature. And they want us to calculate this new diameter of the bubble. So we can use the ideal gas equation, which is going to be PV is equals to NKT. So N and K both will be constant. That's the first thing we have to see. But P will not be constant. We already know that V, the volume and the temperature both are going to be changing, and the pressure will be changing too. The reason is at the bottom of the lake, we're going to have the pressure due to the atmosphere, so the atmospheric pressure, plus the pressure due to the depth of the water. At the surface, there is going to be no pressure due to the depth of the water. When the bubble reaches the surface, there is only going to be pressure due to the atmosphere. So there's only going to be the atmospheric pressure. There's no longer any depth of water, so no longer there's going to be any pressure due to that. Okay, so we have to be very careful with that. Now what we can do, once we know what things are changing, we can say PV over T is equals to constant. We know that this NK right over here, they're going to be constant. So we can say P1 V1 over T1 is equals to the constant, let's say X, and then P2 V2 and T2 is going to be equals to X as well. These values are when the bubble is at the bottom of the lake. These values is when the bubble reaches the surface. So now we equated both of the equations, and now all I have to do is find V2. For the values of T1 and T2, we can add to the 6 degrees Celsius. 6 plus 273, change it into Kelvin, we get 279 Kelvin. Same thing we do with 18, we add 273, it goes from Celsius to Kelvin, 291 Kelvin. And now what we're going to do, we're going to plug all the values in. Remember, P1 is going to be the pressure of atmosphere plus the pressure of the water depth, and then this is just going to be the atmospheric pressure, P2. So I've plugged in all the values. Be careful with the volume of the sphere. That's going to be 4 by 3 pi r cube. Change the diameter and divide by 2 and make it into radius. So be careful with those things. And now all you have to do is find V2. And after calculating it, we're going to get the answer as 4.67 times 10 to the power of minus 9 meter cube. That's going to be the volume when the bubble has reached the surface. Now this is going to be equal to 4 by 3 pi r2 cube. Now I have to find r2, and the value of r2 is going to be equal to the cube root of 4.67 times 10 to the power of minus 9 divided by 4 by 3 pi. And that's going to give me 1.0369 times 10 to the power of minus 3 meter, that's the radius, and we can times it by 2 to give us a diameter. Times by 2, it gives us 2.074 times 10 to the power of minus 3 meters. That's going to be your final answer. I think the main tricky part in this question that might be a little bit not easy to catch when you read the question straight up is the pressure part, but I think besides that, it's not that bad of a question. And now we'll move on to the next part, or the next question actually. It's question number 16. And this is a 6 marker, so it's part of your core practical, I think. So let's just go over the core practical. So this is the core practical 12, and it's about calibrating a thermistor in a potential divider circuit as a thermostat. So this part, the first slide that you can see, is about a little bit about Unit 2, things from your electricity chapter in the AS. So you can just read through it, but it's not that relevant to the core practical. Okay, it says that the thermistor is going to release more electrons. Those are going to increase the number density, and current will increase, and the resistance will decrease, and so your gradient of the IV graph will increase. That's all. You can pause, you can read through it. The main part is the setup. So what we want to do here, the main objective is to plot this curve of temperature and resistance. So we just need different resistances at different temperatures. So different temperatures, we'll just check the resistance, plot a table, get this graph. To do that, we have this setup. This setup is important because remember, we're answering the 6 marker. So the marks you will get is, first of all, you want to make sure the temperature goes really low, 0 degrees. To do that, we put ice. Ice is going to be at 0 degrees. And then to now increase the temperature from 0 to higher temperatures, we can see here, we start at 0, we go till 100. To do that, we're going to put a Bunsen burner. So we put the Bunsen burner down there, and we're going to heat the ice, and the temperature is going to increase. And then at regular intervals, let's say at 0 degree, 10 degree, 20 degree, 30, at those regular intervals, we will measure the resistance and plot the table. To insulate the beaker, to reduce the amount of energy transferred to the environment, we will stir the water to ensure uniform temperature, ensure thermometer is close to the resistor, and read thermometer with high close to and level with scale as well. So these are some things we have to be careful with to ensure accurate values. Okay, so that's going to be a quick run through of the core practical. Now we'll answer the question. So the answer to the 6 marker will be add ice to beaker to decrease temperature to 0 degrees Celsius, heat the beaker with Bunsen burner, record temperature at 10 degrees Celsius regular intervals till 100 degrees Celsius using thermometer, very important. I've put that in black color. And then measure resistance using ohmmeter of corresponding temperature values, stir water to ensure uniform temperature, and then plot curve of resistance against temperature. Pretty standard. That's going to get you your 6 marks. And now I'll show you the mark scheme and the examiner report.